So we're going to take a little bit of time to talk about permutations. Now, permutations are a really important idea, and the word actually tells you what's going on. Permute. Well, permute is talking about changing the order of something, putting something in a new order. So you can imagine you have some ordered list, maybe people standing in line if you like, and you go and say, okay, well, let's rearrange the order of what's going on. Now, when we talk about rearrange, there's two important ideas, and they're closely connected together, and oftentimes we might sort of interchange them, but it's important to recognize that there's two things going on. One thing we can talk about is the sort of final rearrangement. In other words, the end result of carrying out the arranging. But the other thing we can talk about is the rearranging, which is the process. How do we go about and actually rearrange something? And so when we think about a permutation mathematically, it's the process that we actually tend to focus on more than rather the end result. So how do we think about a permutation? Well, one way to think about it is we can think about it as some sort of a function which says, okay, where were you currently and where will you end up? Okay, that's a pretty simple thing. And so if we had n things in order, it would take as our inputs, we could say, well, 1 through n, right? Where are you? And the outputs are 1 through n. And every input has a unique output. So there's actually a name for this. It's a bijective function. Now, how can we write down a permutation? So there's a couple of notations that are fairly common. So let's start with the two-line notation. And this one really emphasizes the process. And what is it? Well, in the first line, you can think of where are things in the current order, all right, the current arrangement of things. The second line says, okay, where are they going to end up? So what you should see is that it says, okay, what's in position 1 will go to position 4. 2 will go to 3, 3 will go to 8, and so forth and so on. So that the number on the top goes to the number on the bottom. That's the rule. So you actually can see the map. Where does everything end up? It's a really nice notation. It emphasizes the idea of, oh, okay, there's this process going on. Now, another common notation that you'll see is one-line notation. They said, look, let's be really efficient. And what we'll do is we'll just say, look, we understand the initial order. We'll just write down the final order and know that, aha, if I know where I started and where I ended, I must know the process that resulted. So the same permutation here, what do you do? Well, you just take that second line. See, the first line is pretty obvious. 1, 2, 3, up to 8. So it's kind of redundant. And so you can imagine going back and forth. So if I had just the one-line notation, I say, well, that's my bottom line. So I realize that, okay, 1 goes to 4, 2 goes to 3, 3 goes to 8, so forth and so on. I could put those numbers there again. All right, so what does this have to do with juggling? Well, in some sense, one of the ways that people have thought about juggling historically is to say, oh, really, juggling is about permuting. So, and one way you can think about it is you have all the points, which are the integers which you can think of as time, and for every point, well, you do a throw. And so you're going to throw it forward and it's going to land at some new point. So you can say, oh, I'm going to map the throw times to the land times. And that's a permutation. It's a one-to-one map. Even if you think about it in terms of that cyclic term, right? In other words, modulo n for periodic patterns. Really what you're doing is, in some sense, you're saying, okay, I'm going to take my throw times and I'm going to look at how they result and connect to my land times. So I'm permuting the two together. And in particular, there's this nice correspondence. So what can you do? Well, you can actually think of turning a permutation into a placement of chess on an n-by-n board. So how does it work? Well, what we'll have is the numbers 1 through n on the rows. Those are our initial inputs, and the columns 1 through 8, those are our outputs, and we say, look, for every input and output pair, we put a rook. So this 1, 4 says put it in row 1, column 4. 2, 3, row 2, column 3. 3, 8, row 3, column 8. And you see, look, everything has a rook in each row because, hey, everything ends up somewhere, and there's only one rook in each row. Why? Well, because if I'm at a current place, I can't somehow split myself and end up in 2 new places, so I can only go to 1 new place. On the other hand, every column also will have a row. Also have a rook. Why is that? Well, if we think about it, we say, look, we started with n objects, we end with n objects, and so we have to have something in every slot. So that says, look, there has to be something in every column. So it's a bona fide rook placement. So we say, aha, beautiful. So we say, look, there's this nice connection between these permutations and our minimal juggling patterns. And in fact, it's very easy to go back and forth between the two. So in some sense, we say, oh, so there is a nice natural connection between juggling and permutations. We'll actually see a little bit more as we go along. There's some interesting things coming. But for now, we're going to spend some time talking about permutations because, of course, there's more to do, more to say, and we should do some practice as well. Now, the first thing we should practice is just sort of getting comfortable using permutations. And remember, it's a process. So we want to think about some examples here and see what we can do. So one thing we can do is we can actually take a sequence of permutations one after another. Now, this makes sense, right? Because we say, well, a permutation just means reorder things. So it's like we start with some initial order, we move them around. Okay, now there's a new order. And then we say, okay, do a new ordering of that. And so we can apply permutations one after another again and again, as many as needed. We can also do an undo, or you might call it an inverse. It says, oh, I changed my mind, I want to go back. So let's do some practice in actually carrying out these kinds of computations. So what can we do? Well, let's write down some permutations. And so we'll use, let's see, we'll just make some numbers up here. 1, 2, 3, 4, 5, and 5, 3, 1, 2, 4. And okay, we'll do another one. 1, 2, 3, 4, 5. And then we'll have 3, 1, 2, 4, 5. There we go. All right, great. So what can we do? Well, suppose we want to look at what happens when we take one after another. So one thing we can sort of think about doing here is we can say, okay, let's suppose we call this one sigma, and we'll call this one tau. Now, why Greek letters? That's kind of tradition. Okay, so let's do what we have this composition, one after another. So what we'll do here, we'll say sigma and tau. So this circle here, that's the same circle that you sometimes see when you talk about function composition, like f of g. And because it's the same idea. See, a permutation, one way to think about it is a function. So it's okay that we use the same notation. So how should you read this? Well, this is sort of the counterintuitive thing. So you have to sort of think about which is the right way to read. Do you read from left to right or from right to left? It matters. And a lot of it comes down to how you use our notation. Now, with this notation, what we'll say is, well, we should really start with doing the tau and then do sigma. So how can we think about our process here? Well, let's just sort of do an intermediate step. So I know if I first apply tau, I have at the top my real first order where I began, 1, 2, 3, 4, 5. And then I apply tau. Well, I know 1 maps to 3, 2 maps to 1, so forth and so on. So I can say underneath 3, 1, 2, 4, 5. All right, great. Now, what happens to do sigma? Well, what I'll do is I'll just continue. Now here, I can't just copy this down because my order is a little bit off. It's been permuted. But it's not so hard to see what's going to happen here, right? 3 is going to map to 1, so we'll put a 1. And 1 maps to 5. 5. 2 maps to what? Maps to 3. And 4 maps to 2. And 5 maps to 4. And there we go. And so really, we say, okay, what's the end result? It's the following: 1, 5, 3, 2, 4. Done, right? Okay, great. Now, what would happen if, say, we did something slightly different? So instead of doing sigma tau, we did tau and sigma. Okay, and now you're like, does it matter? That's a great question. You see, sometimes it doesn't matter the order you do things, and sometimes it does. Let's see what happens here. I don't know. Let's find out. We'll find out together. Okay, so we start with our we start with our initial order, 1, 2, 3, 4, 5, and then first do sigma. All right. Well, we can just copy that. 5, 3, 1, 2, 4. Okay. Now we're going to apply tau. So, well, that just says, look, follow your nose. What happens? Well, we have 5 goes to 5. Okay, so that's a 5. 3 goes to 2. And then 1 goes to 3. 2 goes to 1. And 4 goes to 4. And, okay, again, ignore the middle row. That's sort of an intermediate ordering. And what do we get? 1, 2, 3, 4, 5. And underneath, 5, 2, 3, 1, 4. Are they the same? Well, in bits and pieces they're the same, but they're definitely a different order at the end. So this is a case where order matters. It's one of the interesting things because we're oftentimes so used in early mathematics to be like, oh, order doesn't matter. I don't care which order I add numbers in. I don't care what order I multiply numbers. And so we get so used to this idea, oh yeah, it doesn't matter the order that you do things, that once we actually encounter something where it's like, yeah, order matters a lot, it kind of throws off our game. But now we see, okay, so be careful when applying permutations. Now the other thing that we can do is we can do the inverse. Now it's actually not so hard to do an inverse because what do we want to do? We basically want to exchange, right? We want to say where we started and where we ended, now swap. So in other words, the end becomes the start. So how can you do it? Well, we could say, look, suppose I want to do the inverse of sigma. Well, now just swap the top and the bottom. So 5, 3, 1, 2, 4, 1, 2, 3, 4, 5. And then what will happen is this will definitely undo where we began, right? In other words, it says, hey, if 1 maps to 5, it better be the case that 5 goes back to 1. Well, yeah, that's exactly what we're going to do. Now, what's happening is this doesn't look like our normal 2-line notation because this is out of order. Okay, easy to fix. Now just permute, or rather put in order at the top, right? So, okay, 1 goes to 3, 2 goes to 4, 3 goes to 2, 4 goes to 5, and 5 goes to 1. And done. All right, so great. We have compositions, we have inverses. For those of you who love abstract algebra, and you don't have to enjoy permutations, but you'll say, oh, we're really close to doing things where we have a group. And in fact, permutations do make a very famous group. But if some of those words aren't familiar, don't worry about it. That's another class. So back to our class, our regularly scheduled program. What's another way to think about permutations? Well, there's actually a really good way to think about permutations that we haven't talked about yet. And that's to think about it in terms of cycles. Well, what does that mean? Well, what we mean by this is to say, let's just sort of see where things go to And then where do those go to, and so forth and so on. So let's start with the permutation. This is the same one we started with at the very beginning. So we have, look, 1 goes to 4. Great. So 1 goes to 4. And then, but where does 4 go to? Well, 4 goes to 7. All right? Great. And where does 7 go to? Well, it goes back to 1. And so there we go. And you can see the arrow is indicating where you go. So if I'm at 1, go to 4. At 4, go to 7. At 7, go to 1. Right? So we can see that there's this natural cycle. All right, well, let's see. What's the number we haven't encountered yet? We haven't seen 2. All right, let's see where that takes us. 2. That's going to go to 3, because that's right there. 3. Oh, that's going to be a big jump. Goes to 8. All right, where does 8 go? 8 goes to 6. All right, great. Where does 6 go? Aha, back to 2. Good. Whew, I was in trouble. I was almost about to run out of space. And anything that we haven't seen yet? We haven't seen 5. Okay, where does 5 go? Well, 5 goes back to itself. So it would be what we call a fixed point. Thinking about people standing in line, if we were to rearrange them, a fixed point would be like, oh, somebody who didn't move. They're still in the same position. So 5 goes to 5. There we go. So that's how we can also think about a permutation, is as a collection of cycles. So thinking about these permutations as cycles, we can almost think of it as though we actually have these little knobs that we can twist. And when we do a permutation, or rather if you like apply the permutation once, it's turn the knob. Okay, so I have my 3 knobs, 1 for each cycle. Of course, this knob at the end is not very exciting because it only has 1 setting. But the other ones have multiple settings. So on the outside, let's put our numbers as they currently are. And on the inside, we'll have where things should go. So what do you see here? I'm going to turn my knob here so I have 2 on the top to begin. So what we can see is that initially everything, if we don't apply any permutation, goes to itself. All right, 1 goes to 1, 4 to 4, 7 to 7, so forth and so on. So again, the outside is where you are, the inside is where you should go. So what does applying the permutation correspond to? Well, it corresponds to turning the knobs. Now, which way? Well, what we can say is that we can say a permutation corresponds to applying it. In this case, we're going to go counterclockwise. All right, so we say, look, apply the permutation once. Fantastic. And we turn all our knobs. And of course, that one's pretty easy to turn. And there we go. So we see, aha, 1 goes to 4, 4 goes to 7, 7 goes to 1, 2 goes to 3, 6 goes to 2, so forth and so on. All the knobs are just like we would say. Now, what if we wanted to apply the permutation twice? Well, that's easy. It just says, hey, all you have to do is turn the knob a second time. So in other words, however many times you want to apply that one permutation is how many times you turn your knob. So if we applied it twice, what does it say? Well, it says 1 would go to 7, 7 would go to 4, 4 would go to 1, and so forth and so on. We can actually see where everything goes. Well, if we apply it a third time, we see that we get the following. And don't forget this one on the end. Aha, look. 1 goes to 1, 4 goes to 4, 7 goes back to 7. It's like we're back to where we started. Well, wait, not quite. See, 2 would go to 6. So after 3 applications of the permutation, right, applying the rule 3 times, some parts are back to where they started, but this part is still off. All right, well, what can we do? Well, okay, in some sense we said, look, we got this back to where we started. Well, but this isn't back, so we apply the permutation again. All right, so we apply it one more time, and we say, aha, progress, right? Because now this is back to where it started. 2 goes back to 2, 3 goes to 3. So we've now done it 4 times. But what do you notice? This one is messed up again. Ah! And so you might say, well, okay, apply it again. And you'll see, well, things are still kind of out of order. Now the question is it possible that if you go often enough, will you get back to where you started? And the answer is yes, it is possible. In fact, it will always happen. Now, but what is often enough? So there's a little fun fact, and it says the following. So here's our fact. So if we apply a permutation sufficiently often, now we want to define what sufficiently often means here, and in our case, what it will be what is called the LCM. So LCM stands for least common multiple. So the least common multiple of the lengths of the cycles, then what will happen is we're going to get back to normal. So in other words, we're back to the original order. So why does that work? Well, what happens here is really a simple observation. It says, hey, we saw after we applied our permutation 3 times, so just focusing on this one single cycle. So after we applied the permutation once, twice, 3 times, that part returned to normal. So it says, great. So that says any multiple of 3, that one will return to normal. On this one, it's a cycle of length 4, right? So it would take 1, 2, 3, 4 turns. So any multiple of 4 gets it back to normal. Now here, you're always back to normal because it's a cycle of length 1. So we say, okay, so we just need something which is divisible by 3 and at the same time divisible by 4. Well, that's what the least common multiple does. I should have said also divisible by 1, but everything is divisible by 1. So what is the least common multiple of 3 and 4? In other words, the smallest number which both 3 and 4 divide. The answer is 12. So if you apply this one permutation 12 times, you get back to where you start. Now you'll notice 12 is actually bigger than 8. So it's not the length of the permutation. In fact, you can have a permutation relatively small, but still take many, many, many times if it's just the fact that these cycles somehow are very much out of sync, which forces you to say, oh, I'm going to have to do lots and lots of turning to get things to work out. But it's a really beautiful fact that, hey, if I have any permutation, then applied sufficiently often, I can get back to where I started. Now, one other thing we should say before we go on is that with the cycle notation, it's very hard to put 2 permutations together because once you put permutations together, their different cycles sort of clash and everything sort of disassembles and reassembles. But it turns out it's really easy to talk about inverses. So what did we say? Well, a permutation was a counterclockwise turn. So how do we do the inverse? Well, the answer is to do the inverse. What you do is you just say, aha, change the direction that you turn. In other words, do a clockwise turn. So once I have this set, I say, okay, if I want to figure out the inverse, I will just turn once in a clockwise direction in each one of the cycles. And lo and behold, the result, this is the inverse permutation. In other words, where 1 goes to 7, 7 goes to 4, 4 goes to 1, so forth and so on. So there's a nice sort of, aha, very easy to do inverses in cycle notation. So there's a really nice application of permutations, and that is with shuffling cards. Indeed, in some sense, card shuffling is a wonderful way to think about permuting because that's what a shuffle is doing to the cards. A shuffle is about changing the order or rearranging. And so when you do a shuffle, it's really applying a permutation. And so it's very important to understand the mathematics of permutations if you want to start to get into the mathematics of card shuffling. And of course, this is very, very important. And casinos spend lots of money to make sure, all right, let's make sure our card shuffling machines actually shuffle things very randomly. Because if you're not random, well, that gives an edge to your players. So what you can think of is, all right, you have a deck of cards, here you go, and they come in a pretty standard order. And what you do is you do permutations, you shuffle. And if you shuffle fairly randomly for a couple of times, then what happens is you get something fairly out of order, right? And indeed, it doesn't take too long to get a very random deck. And more or less, there's a belief, and there's a good mathematical proof, that if you were to shuffle a normal deck approximately 7 times with a reasonable riffle shuffle, not too good, not too bad, you don't, well, we'll talk about what not too good means in just a second. Then what you'll have is an arrangement of the deck. And, well, how many arrangements are possible? Well, it's the same as asking the question of how many orderings are possible. If you have n cards, well, you can say, look, n goes into the first, one of n possibilities, n minus 1 possibilities for the second, so forth and so on. So you get n factorial. Now, how big is 52 factorial? The answer is really big, like gigantic. So much so that really not every single arrangement of deck has ever been seen. And so if you were to shuffle a deck multiple times, again, 7 is usually sufficient, I'm not keeping track of how many it is, then what will happen is that unless you're doing something very suspicious, the cards are in an order that's very likely has never been seen before, very likely never will be seen again. And so there you go. Okay, and yeah, that's all kinds of out of order. All right, we've never seen that before. Now, how do magicians do their shuffling? Well, they step in and they say, okay, let's be more careful here. You see, they know that there's many, many possibilities, and they don't want to have to sort of understand all the possibilities, so they want to somehow limit it. Now, why does shuffling work so well? You see, every time you shuffle, you're applying a permutation, but it's a different permutation. There's many, many possible different permutations that can be applied. So what magicians can say is, all right, let's actually take control of our deck, and we're going to focus and only apply one single permutation. All right, well, why? Well, it gives them control, but also we know a nice fact when we apply a single permutation multiple times. So let's start with the deck, and we're going to apply a very particular type of permutation. And so this is, here's our deck, and let's see what our current order is. Okay, spades, diamonds, clubs, hearts, ace to king, king to ace, king to ace. And have some cards in the end, some jokers. We'll take the jokers out. You never want to work with jokers, right? All right, so here's our deck. And what we're going to do is we'll do a quick demonstration of something that's called a Pharaoh shuffle. What's a Pharaoh shuffle? Well, the goal is we're going to take our deck, cut it exactly in half, and then we're going to every other. Now, that's a valid shuffling, and it's a valid permutation. What's important here? Well, we're going to do it very precisely so that we have a permutation. So what we can do now is we can apply it again and again and again. Now, what's the fact? The fact is that if we take our permutation and we apply it multiple times, we must get back to where we started. We know it, right? It's that least common multiple of the cycles. Now, we don't know what the cycles are a priori, but, well, yeah, we can just work our way around, right? All right, so there we go. There's one shuffle. Now, if you've seen this before, you'll know that, not too many shuffles are needed to get back to where you start. This is why magicians like this shuffle. Well, one of two reasons why. See, the first reason is among all shuffles where you actually look like you're shuffling, this one is not so bad to do. It gives the illusion that you're doing a shuffle. So it looks good, and it's fairly easy to learn and control. The second reason is there are other possibilities. We'll talk about one in a second, but this one, it takes not too long for you to get back to where you start. We'll pause for a second here, and we're not back to where we started, and you can say, oh, this is terrible, it's all messed up. Well, not really. Look at the 9s. They're next to queens, then the 6s, and the 9s, and 2, and 3, and 6, and 5. There's this beautiful symmetry. Definitely something very unrandom is happening. Well, of course, because it's us applying the same permutation over and over again. So, as we round our corner here, we're going to get close, and it turns out it just takes 8 shuffles to do it. Now, how do we know? Well, I know because I've seen it before, and I've done it before, but we're going to know because we're actually going to go through and do all 8. And if you're counting, we're really close, actually, and because that was number 7. So here we go, number 8, and lo and behold, what do we see? We see our deck back in the order where we started. Spades, diamonds, clubs, hearts, ace to king, king to ace, king to ace. Almost as good as juggling, right? Yeah. Okay, a good show, right? Math in a show. That's what we should learn. So let's think about what was happening when we were shuffling. So we call this a out shuffle. So why an out shuffle? If you think about the cards on the very outside, the very top, very bottom, okay? So there's the top, there's the bottom. What we were doing is we were shuffling this way. So the cards on the top and the bottom that were on the outside before stay on the outside. So that's why it's called an out. And for some beautiful reason, it turns out that for a deck with 52 cards, that our cycles break up very nicely. So the top and the bottom positions go to the top and the bottom. So that's these cycles of length 1. There's a card roughly about 1/3 of the way down, which swaps places with the card about 2/3 of the way down. And they just sort of hop back and forth. Doom, 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 doom. The rest of the remaining 48 cards break up into 6 different cycles of length 8. And so we have our cycle lengths are 1, 2, and 8. So what's the least common multiple of 1, 2, and 8? The answer is 8. So that says, aha, after 8 applications, lo and behold, we're back to where we started, and that's why we only need to do 8 shuffles. Now, we talked about there's 2 shuffles, right? There's the out shuffle. Well, what's the other one? It would be if you split and the card on the top went into the deck. That's called an in. Well, what happens there? Well, the answer is it's a permutation. It just has a slightly different feel to it. So it turns out that it's a single cycle in terms of the cycle structure. So it's going to take you quite a while. So it's one cycle of length 52. So what does that mean? That says if you took a deck and you wanted to say, let's do in shuffles until we get back to where we started, you'd have to do it 52 times. Now, most magicians don't want to sit there and shuffle for 10 minutes saying, trust me, it's going to be really cool. Just, there's another 47 to go, you know. And most audiences are definitely don't want to see that as well. So that's the reason why whenever you see magicians doing perfect shuffles, they 95% of the time they're doing the out shuffle. There's another 5% of the time when they're not doing, when there's different magic tricks involved. But okay, that's why if you're going to learn to perfectly shuffle, learn the out shuffle first. Much, much easier to do. All right, whew, good, done, yes. Now that we have the language of permutations, it might be good to stop for a few minutes and just say, oh, what are some of the things that we've talked about that we can phrase in terms of permutations? A big thing we talked about was Eulerian numbers, which we said, oh, you think about having a chessboard and you want to place things in the bottom corner below the diagonal. Well, it turns out that that is related to how most people think about Eulerian numbers. So we start with the permutation 1, 2, 3, 4, 5, 6, going to 6, 2, 1, 5, 4, 3, respectively. And of course, we can place them inside our chessboard. And so here we say, all right, well, how many are below the diagonal? And the answer is 3. Now, what do those points below the diagonal correspond to? If you think about what's happening here, if you say, look, let's just pick a number here, 5, right? 5, if I'm in my below the diagonal, says I can go to anything 1, 2, 3, or 4. So in other words, I can go to anything less than 5. It's the same for every number, right? It says, look, like 3 can go to 1 or 2. So what's happening is when we count those things that are below the diagonal, in terms of permutations, what's being counted is how many times did a number end up at a smaller number. So if you're thinking about it in terms of rearrangements, you can say, okay, suppose I have a bunch of people standing in line wanting to get something. Well, I rearrange them, and now the question is, how many people moved closer? That's the number of drops. So that's, I started at some place, and I moved to a smaller number, moved up closer. There's a second idea, and that's called descents. So, well, what's a descent? A descent is the number of times two consecutive values are going to change their position. So, in other words, again, if you have people standing in line, and I have a person who was before me, all of a sudden becomes a person after me, well, that's now a descent. So, how do you find descents? They're actually fairly simple. If we look at our one-line notation, which means just look at the bottom, we say, look for a large number followed by a small number. Okay, so 6 is followed by a 2. That's a descent. 2 by a 1. All right, that's a descent. 5 down to 4, 4 down to 3. So this permutation has 4 different descents. And notice it has 3 different drops. So drops and descents are not the same thing. But here's a really cool fact. It turns out that the Eulerian numbers actually count in some sense both. Well, what do we mean? Well, so the Eulerian number nk is the number of permutations of 1 up to n, so we're talking about rearrangements of n things, where there's exactly k drops. And it's also the number of permutations of 1 up to n, where there are k descents. And so when you hear people talk about the Eulerian numbers, most of the time when they were introduced to it, they say, oh, it's about the descents. That's what the Eulerian numbers are counting. But we saw it, our motivation was in terms of the drops, because that was where we saw, aha, that's our natural connection to counting how many balls that we need in a particular pattern. So again, be careful. Drops and descents are not the same. A single permutation can have different numbers. So let's actually do a really quick computation here to help convince ourselves, hopefully not to confuse ourselves. So we'll write down a permutation, and we'll do it for a small number, 3. So here we'll write down our permutations, and then we have our number of drops and our number of descents. All right, let's do all our permutations. 1, 2, 3, 1, 3, 2, 2, 1, 3, 3, 1, 2. Whoops, I kind of lost my rhythm there. All right, 3, 2, 1. So there we go. Our permutations, our drops, our descents. All right, well, descents are pretty easy in one-line notation, and I'm using one-line notation, well, save space. Okay, so how many descents do we have? 1, 2, 3. None. 1, 3, 2. Oh, 3 went down to 2. Or rather, I should say 3 was followed by a smaller number. 3 to 2, 1. 2 to 1, that's 1. 1 to 3, no. So there's a 1. 3 goes down to 1, then you're going back up. Okay, so there's a 1 there. 2, went up to 3, went down to 1, so there's 1 there. 3 to 2 to 1. All right, down, down, there's 2. So in terms of the number of descents, we see 0, 1, 1, 1, 1, 2. Okay, how about drops? Well, how do we figure that out? We just think about our positions, right? So we're positions 1, 2, 3. We want to just see, is there anything that's mapping to a smaller value? And the answer is, well, no, not for the first one. So 0 again. 1, 3, 2. Now notice 2 is going to 3. That's actually not a drop. That's just going up. All right, but 3 went down to 2. 1. All right, 2 is fine. 2 went down to 1. 3 stayed where it is. So 1 again. 3, that's okay, right? 1 went to 3. That's not a drop. 2 goes to 1. Oh, that's a drop. And 3 goes to 2. That's another drop. So there's actually 2 there. Okay, 2, you're fine because 1 went to 2. 2 went to 3. 3 went to 1. All right, 1 drop where 3 went to 1. 1 went to 3. 2 went to 2. 3 went to 1. All right, 1 drop. All right, so there we go. Number of drops, number of descents. And you'll notice, again, 0, 1, 1, 2, 1, 1, but 1 single 0, 1 single 2, and 4 1. So that's what we mean by they're counting the total number. They count the same, they have the same counts, even though individually there are cases where they differ. So be careful. All right, well, is there another interesting thing that we could count in permutations? Well, the answer is yes. There are, of course, many interesting things that we could count in permutations, but for our purposes, there is one very interesting thing that we want to count, and that's how many cycles we have. So remember that a permutation we can break up in terms of its cycles. So we can say, okay, suppose I have a permutation of 1 through n. How many cycles are there? And more generally, among all the permutations, how many of them have, say, k cycles? Well, that is a number, and that number we call the Stirling number of the first kind. All right, cool. See, we talked about Stirling numbers of the second kind, but we always like, well, hold on. If there's a second kind, what's the first kind? What's the difference between the two? The Stirling number of the second kind says, let's take n objects, which are not ordered at all, and split them up into k groups, which again are not ordered at all. So that's what we're counting. Stirling numbers of the first kind, we say, look, let's take our n objects, which are ordered, split them up into k groups, and in each group, we order them. So ultimately, the big difference between the two comes down to saying, all right, does order matter? That's it. And yeah, in some cases it does, and in some cases it doesn't. Well, of course, once we have a definition, we can get data, right? And we have here the first, quite a bit of the Stirling numbers of the first kind. And you can see there's some interesting patterns that one can spot. For instance, here we have all 1s going along here. So when n equals k, well, what does that mean? Well, that says I want to break 1 up to n, that permutation, and in terms of cycles, I want n cycles. Well, the sum of all the cycles has to add up to n. We have n cycles. That means you can't have any long cycles. Each cycle has to have length exactly 1. And so, what does that mean? Well, it means everything has to go back to where it started. So there's only one cycle that does that. And sometimes you could call that the identity cycle. The cycle that, the permutation that does nothing, right? Okay, well that's a pattern. You might notice these numbers, 1, 3, 6, 10, 15. Those are also familiar numbers. They're the triangle numbers. It's also the way to pick 2 objects out of n. Because here, in this sort of next row, what you need to do is you're allowed to have 1 cycle with 2 elements and everything else is by itself. So, well, how do you form a cycle with 2 elements? The answer is you just need to pick 2 things, right? Because if I have 2 things, I'm going to just jump back and forth. So, all right, great. How many ways to do that? Well, n choose 2. How about the first column. Can we do that? Well, yeah, that's not so bad either. What's going on? Well, look at these numbers. 1, 1, 2, 6, 24, 120. That's getting pretty big pretty fast. Do you recognize those? They're factorials, right? This is 2 factorial, or 2, 3 factorial, 3, so forth on. 4 factorial, 5 factorial, 6 factorial. Well, how does that work? Well, here's how it works. We have one cycle. So what we can do is let's, instead of calling things cycles, we'll just say, look, there's one big table. And we just have to arrange these n things around the table, and we'll arrange them in some direction. Well, we'll go counterclockwise. For some reason, math tends to like counterclockwise things. And the first person, doesn't really matter where they sit. It's a round table. And like, King Arthur and the round table. Look, they're all equal. So it doesn't matter where the first person sits. So, all right, they can sit here. There's our first person. All right. Now, how many choices for the next person to sit to their right? Well, what happens? We already sat one person down, which means that there's going to be n minus 1 choices for the next person, then n minus 2 for the next, n minus 3 for the next, and so forth and so on, until you get all the way around. So it's n minus 1 times n minus 2, which, when you put them all together, makes n minus 1 factorial. Beautiful, beautiful. Now, the Stirling numbers of the first kind also have a similar recursion that we've seen. So how does it work? It says if I want to compute the Stirling number of the first kind, nk, that would be n minus 1 times the Stirling number of the first kind, n minus 1k, plus the Stirling number of the first kind, n minus 1, k minus 1. So how can we think about this? How does it work? Well, let's go back to our putting people at the tables. Okay, so imagine that we have n minus 1 people who are currently seated at tables. And so we have a bunch of tables here. So there's a lot of tables. Some are very small, only have a few people. Some are very large. And around each table are various people are seated. There can even be some tables where there's just one person. And you know what? There might even be an empty table. Okay, so our new person comes in, our nth person. What can they do? Well, what they can do is they can sit down at one of 2 possibilities, generally speaking. One thing is they can say, hey, you know what? I want to be different. So I am going to opt to make a new table. So they go and sit down and they say, aha, here I am. I start a new table. Well, that really means they're going to be in a cycle by themselves. Now, what needs to happen? Well, it's going to introduce one new cycle because every table is a cycle in terms of our analog here. So if I want to end up with a total of k cycles, well, if I add one more, that means I need to start with one less. So I need to have that the n minus 1 people initially were at k minus 1 tables. In other words, that there were exactly k minus 1 cycles. So that's this term right here. So that's that possibility. In other words, the nth element makes something new, a new cycle. Now, what's the other possibility? Well, the other possibility is that our nth person comes in and they sit down at a table where there's already people there. Okay, now, how do we count that? Well, again, in terms of our analogy here, each table is a cycle. If they sit down at a table where people already are, well, there's no new cycles created. So we need to have k cycles originate. So that's why we have this n minus 1k. Where can they sit? Well, the answer is they can sit next to anyone who's currently seated. And more particularly, they can sit to the right of anybody who's currently seated. There are n minus 1 people currently seated, and so our new person coming in picks one of them and sits to their right, there's n minus 1 options. So therefore we have this n minus 1 term. So that's corresponds to that situation. And now we've accounted for everything. So essentially what happens is by thinking about what happens when we introduce that next person, that last element, that helps us figure out the recursion. Well, that's pretty much how all recursions work, actually. It's a nice, simple recursion. And, well, good. So on a final note, and this is really a side note. A lot of what we talk about today, we're not going to really delve into. The Stirling numbers of the first kind, not really many applications in juggling. So if you're like, well, this is a lot to hold in my head, well, that one is one you can let go of a little bit. But I want to point out something interesting. We've talked a little bit about Warpitsky's identity, and that relates to something called x choose n, which is sort of acting like, kind of like a binomial coefficient, but you're allowed to have anything upstairs. So it doesn't have to be a whole number. And so x choose n, it can be x times x minus 1, so forth and so on. You just have n terms on the top. On the bottom, you start with n. You have n terms on the bottom, it becomes n factorial. There's something called falling powers, right? X, the falling power n. Well, what is that? Well, it's x times x minus 1, so forth and so on. So it's like you're taking x, but instead of multiplying x times x times x times x, what happens is every time you multiply, you go down a little bit. It's the numerator of what we had upstairs. So these are sort of algebraic expressions, things involving polynomials. Now, what's the fun thing? If you think about it, we had Warpitsky's identity, which said, hey, you know, I can relate normal powers of x to the n in terms of these binomial coefficients. And what do I need? I need to get the Eulerian numbers, are what helps me go from one to the other. It turns out that the Stirling numbers act in a similar way. So I can do a similar thing that says, hey, you know, if I want to end up with x to the n, I can use the Stirling numbers of the second kind to write x to the n as some combination of these falling powers. But I can also say, hey, maybe I want the falling power written in terms of combinations of powers of x. And there, it's the Stirling numbers of the first kind. So they have this sort of undoingness to each other. One undoes the other. Well, almost. There's this sort of interesting -1 floating around. So what's going on here? What you see is this sort of beautiful blend of algebra, where when we say algebra, we mean things involving polynomials, and combinatorics, which is thought of as things involving counting. So this is, when you put them together, what do you have? You have what's known as algebraic combinatorics. And it's a beautiful field in mathematics, lots of very interesting problems and very interesting results. And but for us, our mostly, we just want to say, hey, this thing exists. And it's a beautiful thing to look at. All right, well, enough digression. We need to get back into doing a little bit more with juggling directly. So we'll pick up again next time.